Tonight, we're going to explore one of the most consequential journeys human beings may ever attempt. Not simply the first crewed landing on Mars, but what happens after the astronauts arrive and discover that coming home is nothing like turning around and retracing the journey. Mars and Earth are constantly moving around the Sun, and the most practical path between them opens only about once every 26 months. That means the first people to reach Mars could spend roughly 500 days on the surface before the planets are positioned for an efficient return. During that time, they would be living farther from Earth than any humans before them, exposed to an environment their bodies were never designed to endure, and by the time a route home finally opens, the astronauts preparing to leave may no longer be the same people who first stepped onto the planet. By the end of tonight, you're going to understand why returning from Mars may be even more difficult than getting there, what nearly a year and a half on another planet could do to the human body, and why the first crew to land on Mars could also become the beginning of humanity's first permanent settlement beyond Earth. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Mars is never a fixed distance from Earth. Both worlds are moving around the Sun, each following its own orbit and traveling at a different speed. As a result, the distance between them changes enormously throughout the year. At their closest, Mars and Earth can be about 54 million kilometers apart. At their farthest, that distance can grow to around 401 million kilometers. On average, they are separated by roughly 225 million kilometers. Imagine driving around the entire Earth more than 5,000 times. That is approximately the distance separating home from the red planet. And distance alone does not determine when a spacecraft can travel between them. A mission cannot simply point toward wherever Mars happens to be and fly there in a straight line. The spacecraft is also orbiting the Sun, and its journey has to intersect with the future position of a planet that is moving the entire time. With current rocket technology, the outward crossing takes roughly 6 to 9 months, half a year at the shortest, most of a year at the longest. During that journey, Earth continues along its orbit. Mars does the same. By the time the spacecraft reaches its destination, the arrangement of the two planets has changed completely. But here is where it gets strange. Arrival does not create the option to leave again. The useful routes between Earth and Mars depend on orbital geometry. That simply means the two planets must reach the right places in their paths at the right time. An economical transfer window appears only about every 26 months. It is like a door that opens for a short while, then closes for more than 2 years. Miss that door, and the crew cannot simply start the engines tomorrow. They wait. The planets keep moving. The geometry has to come back around. For an efficient early mission, that means a surface stay of about 500 days. Think about living through a complete cycle of seasons, then most of another one, knowing the next departure is written into the motion of worlds overhead. So the ordinary timeline begins to look different. 6 to 9 months going out, about 500 days on Mars, then about 8 months coming home. More than 3 years away from Earth. Longer than many people remain in one job, one school, or one home. That length changes the meaning of every small problem. A sore muscle is not just a sore muscle when the next hospital is on another planet. A delayed repair is not just an inconvenience when the replacement parts traveled across interplanetary space. Even a healthy crew cannot treat Mars as a short visit. The schedule makes the place part of their lives for years. And the return date is not a promise. It is an opportunity. The window can arrive only if the people, the habitat, and the spacecraft have all carried the mission safely to that point. And those years do not pass in an ordinary place. Mars has an atmosphere about 100 times thinner than Earth's. The air is not a breathable blanket around the planet. It is a very thin layer of carbon dioxide, offering little protection. Radiation is several times higher than it is on Earth's surface. Temperatures can fall to minus 125 degrees Celsius, cold enough to turn an ordinary winter night into something almost gentle by comparison. Dust storms can spread across the planet and last for months. And Mars has only 0.38 g of Earth's gravity. That last number matters in two opposite ways. A person who lives for a long time in weaker gravity begins to change. Bones, muscles, circulation, balance. The body is built around the pull of Earth, and Mars offers far less of it. But Mars is not weightless. It still pulls downward with more than a third of Earth's gravity. Wait, less gravity does not mean an easy escape. The crew still needs a substantial rocket to rise from the surface. They still need fuel, engines, guidance, and a vehicle waiting to carry them into orbit. Mars is light enough to weaken the body, heavy enough to hold it down. Not an effortless departure, a demanding launch. This is the double constraint. The planet may slowly decondition the traveler who must leave it. The same planet still demands a powerful climb before that traveler can go anywhere. The return is not one flight home. It is a long sequence of timing, hardware, health, and orbital motion. We do not know yet how reversible every change will be after the whole journey. We do not know whether every member of the first cruise will still be medically fit when the next window opens. They may return. Some may choose to stay. Some may find that the option has narrowed before anyone expected it to. And the first slow change may begin long before Mars is beneath their feet. The first of those changes is invisible. Earth supplies protection before we ever notice it. The first shield is the global magnetic field, an invisible region around our planet created deep inside its liquid metal core. It bends away charged particles, tiny pieces of atoms moving at enormous speed from the sun and from deeper space. The second shield is the atmosphere. Above every square meter of ground sits a column of air weighing roughly 10 tons. A patch of air above a space about the size of a small table. That air absorbs and scatters much of what the magnetic field does not turn aside. We evolved beneath both shields. Our cells, our blood, our bones, every slow repair inside the body, developed in that protected place. Mars is different. Billions of years ago, its core cooled and its global magnetic field disappeared. There are small magnetic traces locked into parts of the Martian crust, the outer rock layer of the planet. But those local traces are not a shield around a world. They protect no route between habitats. They do not reach over the whole planet. The atmosphere is also almost absent by Earth standards. Mars has about 0.6% of the surface pressure on Earth. Its protective layer is closer to a thin sheet of paper than a thick blanket of air. The result is a surface radiation level about 40 to 50 times higher than the level at the surface of Earth. A day under that thinner sky can carry what would take many weeks to collect at the lower terrestrial baseline. This is not a distant technical concern. It reaches the body quietly. Radiation is energy moving through tissue. A millisievert, written MSV, is a small accounting unit that estimates how much that energy may matter to a living body. It does not tell us what will happen to one particular person. It helps us add exposure over time. The Curiosity rover carried a dosimeter, an instrument that measures radiation dose. On the Martian surface, it measured about 0.64 MSV per day over several years. That is a little under 2/3 of 1 millisievert each day. On the International Space Station, astronauts receive roughly 0.5 to 1 NSV per day. That may sound similar, but the station still moves inside much of the magnetic protection Earth provides. The most dangerous part of the incoming radiation is still being reduced. The journey through open space is worse. Curiosity measured about 1.8 MSV per day during transit. That is nearly 3 Martian surface days of average exposure collected in one day between the planets. The cruise is not a pause before Mars, it is part of the same dose, and the dose accumulates in 3 long pieces. About 430 MSV during an 8-month trip outward. About 350 MSV during a year and a half on Mars. Then, another 430 MSV during the 8-month trip home. Add those parts slowly. 430. Then 350. Then 430. The nominal mission reaches about 1/200 MSV. That is also 1.2 SV or sieverts. A sievert is simply the larger version of the same biological dose account, like counting the same money in larger bills. The change in units does not change what the body has received. The source compares that total with NASA career limits of 600 MSV for women and about 800 MSV for men. A single mission is therefore more than 1.5 times the lower figure. But here is where it gets strange. Those limits are not a border between danger and safety. They are accepted risk. They are occupational risk. They are not harmless exposure. The limits describe what informed adult volunteers may be permitted to accept during a career. They do not mean radiation below the line leaves no mark, and they do not make a mission above the line impossible. They show that a Mars journey asks for a risk that ordinary life never asks us to carry. One common estimate assigns about a 5.5% additional cancer probability to each sievert. For 1.2 SV, the estimate becomes about 6.6%. Put another way, across a group of 15 people who complete such a mission, the estimate suggests roughly 1 additional cancer case. That is a population calculation, not a verdict on a named astronaut. 14 people might avoid that outcome. 1 person might not. We cannot know which body will carry the cost. So far, this is the slow kind of radiation risk. It is closer to rain falling for years than a single blow. Damage accumulates. Cells repair much of it. Some changes remain. The danger can wait a long time before it appears. But the average can hide the moment that matters most. The sun sometimes produces X-class solar flares, its strongest category of eruption. These events can send charged particles outward fast enough to deliver several sieverts within hours. Not a gradual burden. A sudden dose. Not a future statistic. A medical emergency. There may be only minutes or hours of warning. A crew cannot turn a spacecraft around. It cannot ask Earth to steer through the event in real time. It can only move into the most shielded space available. Perhaps a small protected volume surrounded by supplies and water. That shelter can reduce the dose. It may not make a powerful event safe. This is why average exposure does not settle the question. A mission might experience only the chronic dose we can estimate, or it might meet a rare event that dominates everything else. We do not know which solar weather will arrive during a particular crossing. We do not know how a particular body will respond. The obvious answer is more shielding. But shielding is not one simple layer added at the end. On Mars, the ground itself blocks radiation from below. Burying a habitat or covering it partly with a regolith, the loose soil and broken rock on the surface, can reduce exposure substantially. Water and plastics can also help. They are useful passive shields, meaning material placed between the body and the incoming particles. Every useful layer has a cost. Water sent from Earth adds launch mass. Regolith must be moved by machines or people. A buried habitat takes time to build before it protects anyone. And every EVA, an excursion outside the habitat in a spacesuit, adds dose that no underground room can erase. There is another proposal, active electromagnetic shielding. It would use powerful fields to deflect particles before they strike the spacecraft. In principle, the idea resembles a small artificial version of the magnetic bubble around Earth. In practice, it would demand enormous energy and has not been demonstrated at the scale of a crewed spacecraft. Radioprotective drugs are another possibility. These are medicines intended to reduce some cellular harm from radiation. They remain investigational. They may lessen part of the damage. They cannot make the particles pass harmlessly through a human body. Wait. None of these defenses removes every path of exposure. The soil helps in one direction. Water adds protection. Fields remain unbuilt. Drugs remain partial. And the work outside still continues. That is the hard limit. Radiation can be reduced. It cannot yet be designed away. The first crews would travel beneath a thinner sky and through open space with a risk no complete shield removes, while another unavoidable environment begins changing the same body. Radiation adds something the body was not built to endure. Mars gravity takes something away. It takes away load. The quiet, constant downward pull that has shaped every human body for millions of years. On Earth, that pull is called 1g, 1 standard gravitational acceleration, or 9.8 meters per second squared. It is the acceleration you feel every moment you stand on a kitchen floor. We usually call it weight, but weight is only the sensation. Gravity is the reference setting beneath it. Your skeleton was built under that setting. Your muscles work against it. Your heart pushes blood upward against it. Your blood pressure changes from head to feet because of it. Your inner ear balance system, called the vestibular system, uses it to tell you which way is down. Even the organs inside the body developed in its steady pull. So Mars is not simply a place where you can jump higher. It is a place where the body loses its oldest reference point. Mars has 0.38 g, less than half of Earth gravity. Enough to make movement feel familiar. Perhaps not enough to keep the body fully prepared for home. We have some evidence from the International Space Station. It is evidence from microgravity, the near absence of apparent weight in orbit. The station is not outside gravity. It is falling around Earth so continuously that everything inside falls together. For the body, the result is close to weightlessness. In that environment, bone mass declines by approximately 1 to 1.5% each month, even with intensive exercise. Picture 100 pounds of bone material. After a month, 1 to 1.5 pounds of that support is gone. The loss is not visible from the outside, but the skeleton is being asked to maintain itself without its usual work. Muscles atrophy. They shrink through disuse. Fluids shift toward the head. Faces can swell. Pressure inside the skull, called intracranial pressure, can affect vision. The heart also works against less demand. It does not need to push blood up from the feet in the same familiar way. None of this means Mars will produce the same changes as the space station. Mars gives the body some load. That should be better than zero gravity. But here is where the confidence ends. Humans have lived for long periods at 0g. Humans have lived whole lives at 1g. No one has lived for a year and a half at 0.38g. No one has returned from that life. No one has shown us where the safe threshold lies. The first long stay on Mars would not merely be a mission. It would be the experiment. The crew would be the experiment. Their bodies would provide the first real answer. There are models. A model is a calculated estimate, built from what we know about bone in other conditions. The source describes one possible rate of bone loss on Mars, about 0.5% per month. From every 100 pounds, that is about half a pound each month. Across 18 months, a year and a half, the total reaches roughly 9%, nearly 9 pounds out of every 100. For comparison, normal age-related bone loss is near 1% per year, about 1 pound from every 100 pounds over a year. The source translates the Mars model into a more personal image. After a year and a half on Mars, a traveler might have bones about 9 years older than the calendar says. That is a model, not a measurement. It may overstate the loss. It may understate it. Exercise, medicine, diet, and the body's own ability to adapt may change the outcome. Or they may not change enough. Mars offers no completed human record to settle the question, and bone is only one part of the return problem. Think about what happens when astronauts come home from the station after 6 months. Some need help walking for several days. Many need weeks or months of rehabilitation, meaning supervised work to restore strength and ordinary movement. Their balance must recalibrate, their muscles must grow stronger. Their cardiovascular system, the heart and blood vessels that move blood through the body, must learn Earth again. Some changes to vision may persist. That possibility matters. A return is not finished when a spacecraft reaches the ground. The person inside must also return. A Mars traveler would arrive at that moment after a much longer sequence. About 8 months in zero gravity on the way out. About a year and a half under Mars gravity. Then another 8 months in zero gravity on the way home. Nearly 3 years of altered loading before the body meets 1G again. The return would ask everything at once. Bones must tolerate the forces of ascent and landing. Muscles must work in a seat, then on the ground. The heart must regulate blood pressure through a standing body. The vestibular system must make sense of down again. Vision must remain reliable through entry and landing. Not a simple homecoming. A second adaptation. Not a short recovery. A medical question no Mars crew has answered. But the body has to reach the return ship first. Mars has thin air. There is too little atmosphere for useful aerodynamic lift. The upward support a wing receives by moving through air. A returning crew cannot simply fly from the surface in an aircraft. It needs a dedicated ascent rocket, a vehicle built to rise from Mars and reach orbit. the looping path around a world where the return craft waits. This creates a second trap. The rocket cannot conveniently arrive with the crew. Carrying it along would add too much mass to the outward mission. So it must be sent ahead, placed on Mars before the people who will depend on it arrive. Then it waits. Through dust, through cold, through the long surface stay. For roughly a year and a half, it must remain ready while no one knows whether every valve, fuel line, computer, and engine will behave as intended. On Earth, a first launch failure can mean delay. Engineers inspect the debris. Another rocket is built. A later mission tries again. On Mars, the same failure has a different meaning. No replacement is waiting nearby. No rescue is climbing through the sky. No second attempt may exist. Lower gravity does not remove the need to escape. It weakens the passenger. Then it leaves that passenger dependent on one rocket, after years of waiting, for the only climb away. And beside that rocket, in the small rooms of the base, 6 people would have to live with what a single locked path does to the human mind. That locked path changes the room people live in. 6 people can have food, power, work, and a functioning habitat. They can still lose things the human mind quietly depends on. Connection, new surroundings, a wider social world, and the basic belief that if a place becomes unbearable, you can leave it. Mars removes that last belief. This is what makes isolation there different from a difficult assignment on Earth. A person can endure a hard place differently when a road, a flight, or a rescue remains somewhere beyond the horizon. The option may never be used. It still exists. On Mars, the return vehicle may be waiting outside, but the route home can remain closed for years. The door is visible. It is not open. Antarctica gives us the closest field comparison. Winter over stations hold small groups in extreme cold and darkness, far from ordinary life, with help unavailable for long stretches. They are useful because the people there are not casual volunteers. They are selected, trained, and given serious work. And still, the record is not simple. In stays lasting 6 to 12 months, from half a year to a full year, groups can become more irritable. Some cognitive functions can decline. That means attention, memory, and clear decision-making can become harder. Depression can appear. Small social frictions can grow until every shared meal and every small mistake carries more weight. This does not mean every isolated group breaks apart. It means selection does not erase ordinary human reactions. Competence does not remove resentment. Calmness does not remove loneliness. And a person who is dependable in training may still change after months of seeing the same walls and the same faces. But Antarctica still leaves several anchors in place. The people there breathe Earth air. They see familiar sunlight when the season turns. They know they remain on their own planet. In the most extreme case, an evacuation path exists, however difficult it may be. Mars strips those anchors away. The mission lasts 3 years or more. The crew cannot step outside without a suit. The horizon looks familiar only in the most distant sense. Earth is above them, but it is not available to them. And the knowledge of that distance can become part of every hard day. There is another pattern in long isolation. It is called the third quarter phenomenon. The name describes a decline in mood and function around 3/4 of the way through an isolation period. The beginning is no longer new. The ending can be seen, but it still feels far away. That is the strange point. Morale may not be lowest at the start. The hardest period can arrive after people have already proved that they can endure the mission. The routines feel old. The work feels repetitive. The final stretch seems to move slowly. Not the first shock, the long middle, the visible end that will not arrive. For a Mars crew, that low point would come inside a mission already longer than any Antarctic winter over, and it would arrive in a place no one can abandon. The absence of escape is not background information. It is part of the psychological environment, as real as the thin air outside the habitat. Distance changes help as well. Earth and Mars can be separated by a communication delay of 3 to 22 minutes in one direction. A message can take as long as making a cup of tea, or as long as most of a television program, before anyone hears it. A round trip can take 8 to 44 minutes. A question and its answer can drift apart by nearly the length of a short walk. That turns conversation into asynchronous correspondence. Asynchronous means the exchange does not happen at the same moment for both people. Family calls become recorded words, patient pauses, and replies that arrive after the feeling that created them has shifted. Mission control becomes the same kind of presence. It can advise. It can listen. It cannot sit in the room. But something was wrong. The delay is not only emotional. During a medical emergency, a technical failure, or an acute psychiatric crisis, the crew must decide before Earth can respond. Acute means sudden and serious. A doctor on Earth may receive the first report after the situation has already changed. An engineer may suggest a procedure after the crew has already chosen another one. The people on Mars must diagnose, act, and carry the consequences themselves. They are not supervised explorers. They are an autonomous group. Autonomous means able to make necessary decisions without immediate outside control. Now place 6 people inside that responsibility. The early crew may live in a habitat no larger than a modest apartment for about 3 years. 6 people share every meal, repair, alarm, disappointment, and private silence. There is no separate office across town, no evening away, no new friend arriving to change the balance. Small groups can develop tension within weeks. That does not require malice. Affection can shape alliances. Resentment can shape alliances. Hierarchy disputes can appear, meaning arguments over who has the authority to decide. A minor disagreement about work can become a disagreement about trust. And trust is part of life support. The Antarctic record includes violence, severe depression, and complete interpersonal breakdown among people believed to be resilient. Not because they were careless, because long isolation changes the weight of every relationship. On Mars, there is no replacement crew nearby. No member can be swapped out. If one person becomes unstable, 5 others remain. They must protect that person, protect themselves, and protect the habitat that keeps all of them alive. No psychiatrist can enter through an airlock. No outside authority can take control in person. Delayed advice may help. Procedures may help. But the first response belongs to the people already inside the room. This is why psychology becomes infrastructure. It is not an extra comfort added after the air and water systems are complete. It helps determine whether those systems are used carefully during the worst moment. Planners are developing AI-based mental health tools. AI means computer systems designed to recognize patterns and provide support. They are also considering meditation, mindfulness, structured communication, and mission roles with meaningful autonomy. Mindfulness is deliberate attention to the present moment. Structured communication means agreed ways to speak through conflict before it becomes destructive. These tools may preserve agency. Agency means the feeling that your choices still matter. They may give a crew language for tension before it becomes rupture. They may help a person ask for support before a hard day becomes a dangerous one. But they cannot remove the core condition. 6 people remain together for years in a place they cannot simply leave. The tools can steady the room. They cannot unlock it. And that same limit waits for the body, where a small medical problem can become something much larger. The mind is not the only system whose small strains begin to connect. Mars would place the body under the same kind of quiet pressure. No single change needs to look catastrophic on its own. A poor night of sleep, a slightly weaker heart, a virus that has been sleeping in the body for years, a change in vision. Each one may seem manageable. Together, they may not be. The human body is a complex adaptive system. That means it constantly adjusts to its surroundings. It adjusts to light and darkness. It adjusts to gravity. It adjusts to stress, effort, food, infection, and rest. On Earth, those adjustments happen inside a world that has supported human bodies for all of human history. The immune system shows why this matters. The immune system is the body-wide defense network against infection and abnormal cells. Research from the International Space Station has found that dormant viruses reactivate more often during spaceflight. Herpes simplex, varicella zoster, and Epstein-Barr virus have all appeared more often in astronauts than in comparable people on Earth. Dormant means The virus is already present but quiet. It has not left the body. It is waiting. Scientists have also found changes in cytokines and natural killer cell activity. Cytokines are chemical signals that tell immune cells where to go and what to do. Natural killer cells are part of the body's cellular patrol. They help find infected cells and cells that have begun to behave abnormally. We do not fully understand why this happens. Stress hormones may be part of it. So may disrupted sleep. Circadian disruption may matter too. Circadian means the daily body clock that expects light, darkness, rest, and activity to arrive in a familiar order. Low gravity may change immune behavior. Radiation may damage immune cells directly. An infection may become harder to contain. A dormant virus may wake up. Healing may slow down. Cancer surveillance may weaken. Cancer surveillance is the immune system's quiet work of finding dangerous cells before they can grow unchecked. This is not one dramatic failure. It is a lower margin, a body with less room to absorb the next problem. The heart faces its own adjustment. On Earth, every heartbeat pushes blood upward against gravity. In low gravity, that burden changes. The heart can become smaller and less efficient because it is doing a different kind of work for months and years. Blood pressure regulation can change as well. This means the body may struggle to keep blood moving where it needs to go when gravity pulls it downward again. There is also concern about arrhythmias. An arrhythmia is a heartbeat that becomes irregular. Some of the structural changes seen after long missions reverse after return to Earth. Some may not reverse completely. We do not know how a particular heart will respond after a much longer journey that includes both weightlessness and Mars gravity. Then, there is the eye. Spaceflight-associated neuroocular syndrome is called SANS. It is a condition involving the nerves and structures of the eye during long exposure to low gravity. After 6 months on the International Space Station, about 70% of astronauts show some degree of it. That is roughly 7 places at a kitchen table set for 10. The syndrome can involve swelling of the optic nerve. The optic nerve carries visual information from the eye to the brain. It can flatten the back of the eyeball. It can reduce visual acuity, which means the sharpness of what a person sees. In some cases, the changes do not fully reverse after return. The leading explanation involves a cephalad fluid shift. The name sounds technical. It means body fluid moves toward the head when gravity is no longer pulling it down toward the feet. That movement may raise pressure around the head, with some of that pressure reaching the eye. The picture did not hold. Mars is not weightless. Mars has 0.38 g. The fluid shift may be smaller there. It may not disappear. No human has lived for an extended period at that gravity, so no one can say how often SANS would appear or how severe it would become. Not a solved problem. A missing measurement. A question carried by the first crew. Poor vision is not a small inconvenience on Mars. It can affect delicate repair work. It can affect readings on instruments. It can affect the ability to work safely outside the habitat. And later, it can affect the ability to monitor a return vehicle when every screen and control matters. This is the point where separate medical lists stop being useful. The changes form a network. Radiation can harm immunity. Weakened immunity can slow healing and reduce cancer surveillance. Cardiac decline can limit exercise. Less exercise can worsen bone loss. Weaker bones raise fracture risk. A fracture can limit work outside the habitat. SANS can reduce technical ability. Reduced ability and uncertainty can raise stress, and stress can feed back into immune dysfunction. Each link is modest. The chain is not. The crew would not face that chain inside a hospital. A Mars habitat can carry medicines and medical tools. It can carry a trained medical officer. But the medical officer would be an astronaut with broad medical preparation, not a specialist surgeon, cardiologist, eye doctor, infectious disease physician, and pharmacist at the same time. There would be no large imaging suite, no full surgical team, no infinite pharmacy. Imaging means seeing inside the body with specialized machines. A large imaging suite is the equipment a hospital uses to search for injuries and disease that cannot be seen from the outside. Earth specialists could still help. They could review records and offer advice after the communication delay, but they could not examine the patient in person. They could not bring a new machine through the airlock. They could not send a replacement medicine the moment the last dose is used. Drugs run down, tests run down, sterile supplies run down, equipment can fail, and every spare part must have been selected long before anyone knows what illness will appear. But the reality was different. The deeper danger may not be an emergency at all. It may be accumulation. It may be interaction. It may be a crew that remains alive and functional, yet slowly becomes less able to meet the next demand. That is what makes the medical problem so difficult. An isolated infection may be treatable. A single irregular heartbeat may be monitored. A modest loss of vision may be adapted to. But those changes can arrive in the same person, alongside radiation exposure, bone loss, poor sleep, and the strain of an unleavable mission. The habitat has finite resources. The body has finite reserves. And the mission still asks for its hardest physical work at the end. A crew may land successfully. It may work on Mars for years. It may keep the habitat alive. Yet by the time ascent, transit, re-entry, landing, and rehabilitation arrive, the people inside it may no longer be the people who left Earth. The cost is not hypothetical. The exact shape of it is still unknown. And that leaves a harder question waiting beyond the medical ledger. What could make an informed person decide the journey is worth it? If the cost is this real, the reason for paying it has to be real as well. The question changes. What could a person find on Mars that makes the possibility of never returning an informed choice? The first answer has to be honest. Early Mars missions may carry a meaningful chance that some participants die there or remain there, despite a productive mission. Mission literature does not always place that possibility at the center of the picture. Launches, habitats, rockets, and return windows are easier to describe, but the architecture has limits. A return rocket waits on the surface. A launch window arrives only after about 26 months. Radiation accumulates. Bodies change. The chance that every person returns is not certainty. That is not a forecast of failure. It is a condition of the first attempt. Some advocates have said this openly. Elon Musk has said that early participants should be prepared to die. That statement does not establish a return percentage. It does something more limited. It acknowledges that frontier travel can involve a risk that careful language sometimes leaves in the background. Human beings have accepted dangerous journeys before. Polar expeditions, ocean voyages, and mountaineering all carried known mortality risk. But Mars is different. The old expeditions could fail to return. Mars can make non-return part of the structure itself. A ship cannot simply turn toward home. A crew cannot call for a rescue flight. A person can survive, keep working, and still lose physical access to everyone and everything that once made up ordinary life. That is a different kind of risk. Soldiers generally expect to return if they survive. A person with terminal illness has not volunteered for the illness. Neither comparison quite reaches Mars. The closest source analogy may be the first voyages into unknown oceans, undertaken without an assured return. Even then, the ocean was still part of Earth. The traveler remained beneath a familiar sky, breathing familiar air. On Mars, the separation would be more complete. Family messages would arrive after delay. Rain, trees, crowds, rivers, ordinary weather, all would belong to another world. The person might remain alive for decades. The distance would remain. Not a brief hardship, a new life. And some people may still choose it. The crew would not have to be tricked into sacrifice. They could understand the probability and the limits of the medical evidence. Then they could decide that the destination, the work, and the contribution are worth the chance. The reason begins with the world itself. It has a soul, the length of one Martian day, of about 24 hours and 37 minutes. The extra 37 minutes is about the time it takes to make dinner or finish a short walk. A crew could follow a rhythm close to the one human bodies learned on Earth. It has seasons. Its axial tilt, the angle of its spin, gives different parts of the planet changing amounts of sunlight through the year. It has polar caps. It has ancient river channels. It has lake beds, the remains of places where water once gathered and stayed. For possibly hundreds of millions of years, liquid water may have lasted across parts of its surface. That is not a small geological detail. It is a long chapter of planetary history, long enough for a basic question to become unavoidable. Did life ever begin there? That question changes the meaning of every rock. Mars has Olympus Mons, a volcano about 22 kilometers high. It is the tallest volcano in the solar system. It has Valles Marineris, a canyon system about 4,000 kilometers long, roughly the length of the continental United States. These are not features that fit comfortably inside the idea of a barren outpost. They make Mars a whole world, with landscapes large enough to hold its own history. And that history may still be readable. Robotic missions can take photographs, drill cores, and test minerals with astonishing precision. But a human geologist can see a broken layer of rock, notice an unusual pattern, and change the next sample on the spot. Field judgment means using the eyes, tools, and surrounding landscape together. On Mars, that flexibility has special value. A message to Earth can take minutes to arrive. Advice returns later. A rover may wait. A person standing beside an ancient riverbed could look in 3 directions, compare layers, pick up an unexpected stone, and decide what deserves attention next. But here is the deeper prize. The search is not only for a fossil or a chemical trace, it is for evidence that life arose somewhere other than Earth. One sample could matter, one layer could matter, one preserved environment could matter, not a tourist destination, a second test of life. If Mars once had its own biology, even simple biology, our picture of the universe changes. Life would no longer look like a single event confined to one fortunate planet. It would look more possible, perhaps more common, perhaps still rare. We would need more evidence before claiming either answer. But the question would become larger than our planet. That possibility cannot make the risks harmless. It can make them intelligible to someone who chooses to take them. There is a second reason, and it reaches beyond science. For now, all of humanity lives on one planet. A single planetary home has obvious strengths. It also has a single point of failure. An asteroid impact, a pandemic, nuclear war, or climate collapse could affect the only place where our species lives. Mars would not instantly solve that problem. A small habitat dependent on supplies from Earth is not a second civilization. It is an outpost. It remains connected to the same vulnerable world it is meant to supplement. The conclusion points elsewhere. That is exactly why the first crew matters. Their deepest success may not be a perfect round trip. It may be the systems they leave behind. A stronger habitat, better local water extraction, more reliable food production, better records of how bodies adapt, better evidence about which risks can be reduced and which ones cannot. The first people would build knowledge, they would build capability, they would build a place others could inherit. That is what species redundancy means. It means having more than one place where human life can continue. Not an escape from Earth, not a replacement for Earth. A second foothold, able one day to keep going if the first is injured. Whether such a settlement can become genuinely self-sustaining remains unknown. Self-sustaining means it can maintain its people without constant support from Earth. No early base would begin there. It would begin with machines, stores, uncertainty, and an enormous dependence on systems that have never operated for years in that environment. But every durable human presence begins before it is durable. The first mission may therefore be measured in 2 ways. One measure is painfully personal. Did each person come home? The other measure looks forward. Did they make it more likely that later people could survive, return, and remain by choice? Neither measure cancels the other. A lost return is still a loss. A permanent separation is still permanent. Yet a crew may accomplish unprecedented science, establish the first working foundation, and change the prospects of everyone who follows. Not a failed journey. A foundation under terrible conditions. And a foundation begins with a smaller question, whether the people who arrive can keep making air, water, and food on a world that supplies none of them freely. A second foothold begins with a much smaller fact. 4 people have to keep breathing. On Mars, the air outside cannot help them do that. It is about 95.3% carbon dioxide, 2.7% nitrogen, 1.6% argon, and only about 0.13% oxygen. Out of every 1,000 gas molecules, only about 1 carries the oxygen a human body needs. The rest are mostly carbon dioxide, and the air is almost absent in another sense. Mars has a surface pressure of about 600 pascals. Earth at sea level has a 101,325 pascals. If Earth's air pressure were divided into 1,000 equal portions, Mars would have fewer than 1. Even a container filled with pure oxygen at that pressure could not keep a person conscious. The comparison is severe. Standing on the Martian surface is roughly like standing 35 kilometers above Earth, above 99% of the atmosphere. It is deep in the death zone. The problem is not merely that the wrong gas is present. There is too little gas of any kind pressing on the body. So the real human environment on Mars is a pressure vessel. It is a manufactured room that holds the right pressure, the right gas mixture, and the right temperature. It must pull carbon dioxide out of exhaled breath. It must replace oxygen. It must keep doing both while dust settles on equipment, cold works through seals, and every spare part has been carried from another planet. We have experience with parts of this problem. The International Space Station has maintained pressure vessels and carbon dioxide scrubbers for more than 20 years, longer than it takes a child to grow into an adult. But the station is not Mars. A major failure there may still leave a Soyuz capsule as an emergency route home. Mars has no such exit. That changes the meaning of a broken machine. If carbon dioxide removal stops, the gas the crew exhales begins to build. If oxygen generation stops, the useful fraction begins to fall. The failure does not have to wait for a distant rescue mission. Without redundancy or repair, it can become fatal within hours, before breakfast has become lunch. The air outside, however, contains the raw ingredient for one part of the answer. It is mostly carbon dioxide, and carbon dioxide can be split apart. Perseverance carried an experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. In situ resource utilization means making useful supplies where you are, instead of bringing every supply from home. MOXIE used solid oxide electrolysis. That is a process that uses heat and electricity to separate oxygen from carbon dioxide. It worked. But here is the scale of the result. MOXIE produced up to about 10 grams of oxygen per hour. That is about the mass of 2 teaspoons of water. The source estimate for 4 people breathing is about 2,000 grams per hour, about the mass of 2 full-liter bottles of water. One small machine, 200 times too small. The chemistry is real, the gap is real, the years are still unknown. That distinction matters. A device can prove that Mars offers oxygen feedstock. It has not yet proved that a much larger version can run for years without interruption, while a crew depends on it every minute. A machine sent ahead of the crew might one day close the gap. We do not know yet whether it can do so with the reserve margin a human mission requires. Water follows the same pattern. A person needs roughly 2 to 3 liters for drinking each day, about 1 large bottle to 1.5 large bottles. Then come washing, food preparation, medicine, and agriculture. Across 1,000 days, almost 3 years, shipping every drop becomes a major mass problem. Mars appears to hold water in several forms. The Phoenix lander found ice in 2008, only a few centimeters below the soil at its northern site, about the width of 2 fingers. Curiosity found hydrated minerals in Gale Crater. Hydrated minerals are rocks that hold water within their structure. Perseverance found them in Jezero Crater. Orbital radar has also seen a feature that may be a liquid water lake beneath the south polar ice cap. At first, this seems reassuring. Ice exists, water-bearing rock exists, a possible lake may exist. Then the data shifted. Discovered water is not usable water. Planetary abundance is not a supply line. A crew depends on one location. The selected landing site must contain ice or water-bearing material in a useful concentration. It must be close enough to reach. It must be possible to excavate. Then, the extraction equipment must survive dust, cold, wear, and limited maintenance. A map showing ice somewhere on Mars cannot fill a tank at the habitat. That is the site-specific reveal. Mars may have enormous stores of water. The crew may still land on dry soil. And the difference between those statements could be a fatal shortfall. Food carries a quieter version of the same risk. Packaged food can be dried and dense. It can also be counted and stored. Yet enough food for 1,000 days remains a large launch burden. A mission that wants to stay longer has to consider growing something locally. The Martian regolith, the loose broken material covering the ground, contains minerals plants use. But it also contains perchlorates, reactive salts that can be harmful to people and plants. Biological remediation means using living systems to reduce or remove that contamination. It may be possible. It is not the same as having a reliable farm. No agricultural system has supplied a meaningful human diet under Martian pressure, radiation, gravity, power limits, and closed-loop conditions. Fresh crops would matter. They would add nutrition. They would break the monotony of packaged space food. They might support morale in an enclosed world. They could also fail. A disease, a pump problem, a loss of power, or a damaged growing chamber could turn a hopeful garden into another emergency. Not a supplement then, a dependency. This is the design trap at the center of the mission. The safest architecture carries large reserves of air, water, and food from Earth. That reduces dependence on local machinery. But every reserve adds mass. More mass means larger launches, more cost, and more complex missions. The more affordable architecture does the opposite. It brings less and makes more on Mars. It uses local oxygen, local water, and perhaps local food. That lowers launch mass. It also gives each extractor, scrubber, pump, and crop system a larger share of the crew's survival. Neither choice is simply wrong. Neither choice is fully safe. One path can become too heavy to build. The other can become too fragile to trust. No current architecture makes cost and operational risk small at the same time. And even a habitat that finds the right balance may still face the part of the return journey that no machine can fully protect. Suppose every one of those systems works. The oxygen system works. The water system works. The food stores and growing chambers work. The Mars ascent vehicle launches when it is meant to launch. The Earth return vehicle receives the crew in orbit. Nothing breaks in the simple, dramatic way we usually imagine. And still, someone may not come home. This is one of the most troubling possibilities in long-duration spaceflight. The mission can succeed as an engineering project and fail as a return journey for a human being. Not the rocket, the passenger. Picture the nominal sequence. The crew spends 8 months traveling outward. It lands safely. It lives and works on Mars for about 500 days. It climbs back to orbit in the ascent vehicle. It meets the return ship. Then it spends another 8 months crossing the dark space between the planets before entering Earth's atmosphere and landing after roughly 3 years away. Every stage can go according to plan. Yet the plan changes the people carrying it out. By the time the crew approaches Earth, each person has accumulated a history inside the body. Radiation exposure has passed the career limits discussed for early Mars missions. Bone and muscle have spent years under lower loads. The cardiovascular system, the heart and blood vessels that move blood through the body, has adapted to doing less work against gravity. The immune system, the network that recognizes infection and helps control abnormal cells, has been altered by long spaceflight. And some crew members may have SAENS, spaceflight-associated neuroocular syndrome, a group of changes involving fluids, pressure, and vision. None of this means every traveler becomes unable to return. That is not what the evidence says. The trouble is more precise. Each body responds differently. A risk spread across a crew is not a prediction for one person, but an individual person may still have the severe response. The most demanding encounter with gravity may come at the end. Earth re-entry can impose several times normal terrestrial gravity, depending on the path through the atmosphere and the vehicle. That force presses blood toward the feet. It loads the chest. It loads the spine. It asks the muscles to hold the body steady. It asks the balance system to make sense of a world that has suddenly become heavy again. The proprioceptive system helps a person know where their limbs are without looking. It is the quiet sense that lets you close your eyes and still touch your nose. After months in weightlessness and a long stay at 0.38 G, that system has been learning a different set of cues. The heart has also been living in a different environment. So have the bones. So have the muscles. Then the capsule begins to fall. The highest demand, the weakest moment, the heaviest world. There is already a smaller version of this problem on the International Space Station. Some astronauts returning after only 6 months have briefly lost consciousness during landing. The cause can be orthostatic hypertension, the inability to keep blood pressure high enough when gravity pulls blood downward. On Earth, the circulatory system makes constant adjustments whenever we stand. After time in space, that adjustment can lag behind. 6 months is not 3 years, and no human has spent 3 years away from Earth's gravity. That missing experience matters more than any confident projection. We have measurements from astronauts in orbit. We have models of partial gravity. We have evidence from rehabilitation. We do not have a Mars-returning body coming through Earth's atmosphere. After that exact sequence of weightlessness, Mars gravity, radiation, confinement, and another long transit. So the central question remains open. Can a body adapted to Mars reliably endure ascent, re-entry, landing, and life at 1G again? We do not know yet. But here is the harder possibility. The answer may not be the same for every member of the crew. One person may begin with a vulnerability that was invisible in training. Another may lose bone more quickly than expected. Another may develop a more serious cardiovascular response. Another may have vision changes that make the return sequence less safe. A mission doctor and the crew could face a quiet, terrible judgment. The available seat is there. The vehicle is ready. But one body may not be able to use it. This is sometimes described as a physiological point of no return. Physiological means connected to how a living body functions. The phrase does not name a measured Martian boundary. No one can point to a day on a calendar and say that crossing it makes Earth impossible. It names a serious medical scenario. Extended life at 0.38 G may leave some people so changed that returning to Earth becomes medically inadvisable or medically impossible. The uncertainty is not strange. Human adaptation is rarely all or nothing. Think about people who live at high altitude for years. Their bodies can make more red blood cells and become better at taking oxygen from thin air. When they move away, some changes reverse quickly. Others can linger. The body is not a switch that flips back at the airport. A long sedentary life offers another, quieter comparison. Years without demanding the full strength of the heart, lungs, and muscles can leave persistent marks. Exercise can help. Rehabilitation can help. But recovery has its own timetable, and not every change disappears completely. Reduced gravity may work the same way. Bone remodeling, the slow process by which bone tissue is rebuilt, can take years. Muscle can require months of therapy. Cardiovascular recovery can require long aerobic rehabilitation, meaning gradual exercise that trains the heart and lungs to work over sustained periods. SANS may persist. In serious cases, it may require treatment or leave lasting vision impairment. Not a short recovery, a long uncertainty. A body changed by residence, and the physical question is only half of it. 3 years on Mars would not resemble a long work assignment in orbit. The crew would wake beneath an alien sky. It would move through a lighter world. The horizon would sit closer than the open sweep of an earthly plane. Outside the habitat, the silence would be profound. Messages from home would arrive after the moment that produced them had already passed. Those conditions do more than test endurance. They can change belonging. Astronauts returning from 6-month missions have already described a kind of dislocation. Familiar streets and crowded rooms can feel strange after living above Earth, even while seeing the planet outside a window and speaking with family in real time. A Mars crew would have neither continuity. It would share work no one else can fully understand. It would make repairs in dust and cold together. It would learn the rhythms of one small habitat and one distant landscape together. Antarctic expeditioners and submariners offer partial hints. People in extreme environments can form durable bonds with the place and the small group that help them survive. Mars would be different from either of those places. It would be farther away. It would be harder to leave. But the attachment may be deeper for exactly that reason. For some, Earth would remain the center of gravity in every sense. They would want to return because they can, because they miss the people and places that formed them, and because the mission was always meant to end there. For others, return may remain a duty. A crew member may be medically cleared and emotionally torn, yet still take the seat because families, institutions, future crews, and the promise of shared knowledge all call them home. And some may stay, not because they have been abandoned, not because every system has failed. They may stay because unfinished work matters more than the familiar world, because the people beside them have become their closest human bond, because Mars, slowly and unexpectedly, has become home. That is the final reveal inside a nominal mission. A functioning vehicle does not guarantee a returning person. Medical limits can close the path, so can a willing heart. And when even one person remains, the question is no longer only how to visit Mars, but how a small outpost begins to become a community. One person staying is a choice. A place able to receive the next person is the beginning of something else. That place would not look like the Mars cities of old illustrations. No glass towers, no wide streets, no open parks beneath a changed sky. The first durable base would probably begin with inflatable living modules and rigid prefabricated rooms delivered before the crew. Together, those rooms might contain roughly 100 to 500 cubic meters of pressurized space. That is the scale of a modest apartment at one end, or a large house at the other. 4 to 6 people would share it. Sleep would happen there. Meals would happen there. So would work, exercise, medical care, mission control, recreation, arguments, repairs, and the long quiet hours between them. Almost every unsuited moment would happen inside the same small volume. This is the first correction to the image of settlement. Not a city, a foothold. Not freedom from the habitat, a life enclosed by it. The habitat would need to disappear beneath the surface almost as soon as it arrived. Robotic equipment could push Martian regolith over the modules before people land. Regolith means the loose dust, grit, and broken rock covering the ground. Several meters of it would place more material between the crew and gamma radiation, the deeply penetrating radiation released by unstable atoms, and cosmic radiation arriving from beyond the solar system. It would reduce the dose, it would not erase it. Power would have to keep flowing when the planet turns against solar panels. Global dust storms can suppress sunlight for weeks or months. That makes a kilopower-class fission system an important candidate for the base. Fission means splitting heavy atoms to release heat, which can then become electricity. Unlike solar panels, it does not wait for a clear sky. An array of such systems could make the buried rooms livable. Air circulation, water pumps, heating, lights, computers. The slow machinery that turns a sealed shelter into a place where people can remain. But the machinery must prove itself before the first person trusts it. Water systems could arrive months ahead of the crew. Robots would drill into ice-bearing regolith, heat the material, and condense the released vapor into water. Oxygen systems derived from MOXIE could take carbon dioxide from the Martian air and separate out oxygen. MOXIE was a small experiment that showed this chemistry can work on Mars. For a settlement, the important achievement would not be a full tank. It would be a long record of ordinary operation. Dust on seals, cold in pipes, radiation reaching electronics, wear inside pumps, repairs carried out with the tools already there. This is called in situ resource utilization, using materials found at the destination instead of carrying every useful thing from Earth. On Mars, it would mean making water and oxygen where they are needed. But the real test is continuity. The machines would have to work through the conditions that would eventually challenge the crew. For months. Before dependence begins. Not a demonstration. a commitment. Communication would mark another quiet change. The base could use direct radio to Earth and relay satellites circling Mars. Yet a message would still need from 3 to 22 minutes to travel one way, depending on the planet's positions. That delay has already shaped the emotional life of the mission. Here it would shape the work itself. Time-critical decisions would happen locally. A torn suit seal, a failed pump, a medical change, an unexpected signal in the field. Earth could advise, but it could not take the next action in real time. That is a different kind of exploration. The crew would not merely operate equipment sent from home. It would become the immediate authority for a living system far beyond home. And that authority would matter most outside the habitat. A rover can travel carefully, photograph a surface, and send its findings across the distance. But a human geologist can stand beside an outcrop, a visible layer of exposed rock, and change the plan in hours. A rover may need months for the same contextual judgment. The person can notice a fracture, trace a mineral pattern, compare layers, and decide where the next sample should come from while the evidence is still in view. Mars has ancient lake beds and riverbeds. It has hydrothermal deposits, minerals left behind by hot water moving through rock. It has protected subsurface zones where water may still exist, or where traces of ancient life may have survived the surface. These are not simply places to visit. They are questions held in stone. Did Mars ever support life? Did life begin there independently? If the answer lies in one particular layer, a field team might spend years learning how to read it. Then the departure window arrives. The geometry does not care whether the work is complete. It does not care whether the next outcrop is 10 meters away. It does not care whether a sample has just made the larger question more urgent. The orbital opportunity opens, and an early crew is expected to leave. But the work does not end. The habitat needs maintenance. The water equipment needs watching. The science continues through the next season, then the next launch window. A resident who stays is not simply refusing a return flight. That person may be preserving a chain of attention that no replacement crew can instantly inherit. This is where an expedition begins to gather weight. A base becomes more than its rooms when its systems hold history. Which pipe has needed repair twice? Which field route is safest in the dust season? Which sample bed deserves another month? Which small habit keeps a crew working together? Still, 4 to 6 people cannot make a self-supporting society. They can maintain a fragile beginning. A true settlement would eventually need enough people to preserve knowledge across power, air, water, medicine, agriculture, maintenance, and governance, the shared rules used to make decisions. Estimates range from a few hundred people to several thousand. That span is the difference between a small village and a small town. The uncertainty is not a failure of counting. It reflects different assumptions about automation, machinery, and the range of skills that must remain available when a specialist is sick, tired, or gone. Redundancy would no longer mean only spare pumps and spare filters. It would mean more than one person who understands the reactor, more than one person who can treat an illness, and more than one person who can repair a pressure seal, grow food, teach a child, settle a dispute, and preserve the record of what the settlement has learned. That is the deeper threshold. Not a larger habitat, a larger human memory. As that memory grows, return may remain technically possible while becoming less central. People could still look toward Earth. Supplies could still arrive. Families could still speak across the delay. But the daily work, the local friendships, and the future plans would increasingly belong to Mars. Then comes the generational change. The first adults who do not return would choose or accept the outcome. Their children would inherit it. A child born under Zedulking 38G would not begin with Earth as a remembered home. The difficult question of whether that child could safely live at Earth gravity remains unanswered. For now, it remains beyond the edge of our evidence. But even before that answer is known, a culture could be taking shape. Its stories would begin with the first buried rooms. Its ordinary skills would include surviving dust, tending machines, and reading a landscape older than any human city. Its idea of distance would include a blue world visible only as a destination for messages and rare travelers. Earth would still matter. It would be where the first people came from. It would be the ancestral world, as Europe can be ancestral to Americans without being home. But for the descendants of the first stayers, Mars may become the place that gives the word home its immediate meaning. Before we follow that future any farther, we have to separate what Mars has shown us from what we are still only projecting. Before we follow that future any farther, it helps to separate what we know from what Mars has never allowed us to measure. The distinction is not a technical footnote. It is the center of the decision. A settlement, a Martian childhood, a blue Earth becoming ancestral, all of that reaches beyond the evidence we have today. Some parts rest on hard observations, some rest on careful inference, some remain unanswered, and some questions have not appeared yet. This is the unfavorable ledger. Start with what is established. A round trip lasting roughly 3 years would accumulate a radiation dose beyond the cited astronaut career limits. That does not prove a particular person will become ill. It does establish that the mission enters a range already treated as an accepted occupational risk, rather than a harmless one. Reduced gravity also changes the body. Bone responds to mechanical load, the repeated pull and pressure that tell living tissue how strong it must remain. Give bones less load for long enough, and they lose material. Mars offers 0.38 g. We know the direction of the change. We do not know its exact rate there. The heart and blood vessels change as well. In low gravity, the cardiovascular system, the network that moves blood through the body, does not work against the same constant pull. It adapts to a different world. A traveler returning to Earth would arrive with a body shaped by that altered demand. Vision belongs on the established side of the ledger too. Spaceflight-associated neuroocular syndrome, called SANS, involves changes to the eyes and vision during long missions. It affects a large majority of astronauts on long stays aboard the International Space Station. Some effects have persisted after return. Mars has not answered whether partial gravity changes that pattern, or merely changes its shape. And the ascent vehicle remains a fact of a different kind. The Mars ascent vehicle is the rocket that would lift the crew from the surface to orbit. It must work when its moment comes. There is no immediate rescue. There is no spare vehicle arriving tomorrow. The first operational use has to be enough. These are not guesses. They are the known hazards. But the known hazards do not add together as neatly as a column of numbers. Radiation may affect tissues already stressed by altered gravity. Poor sleep may weaken attention during maintenance. Isolation may shape immune function, mood, and judgment at the same time. A non-linear interaction means the combined effect can be larger, or simply different, than the separate effects suggest. This is where the ledger becomes uncomfortable. We can study each pressure. We can build models of several pressures together. But no simulation can place a particular human body through years of transit, 0.38 g, radiation, isolation, and surface work. Then ask it to climb into a rocket and endure Earth again. Not a missing calculation, an unrepeatable trial. The long-term effects of Martian gravity remain one such unknown. Earth gravity gives us one end of the scale, weightlessness gives us another. Mars sits between them. No person has spent years living there. The first crew would not merely test a prediction, it would create the first human evidence. The same is true of individual return fitness. One person may preserve enough bone, circulation, vision, and strength to make the journey home. Another may decline more sharply. Which person will be affected most? At what point? After what combination of stresses? Those answers may only emerge while the mission is already underway. Solar weather adds another uncertainty. We can observe the sun. We can receive warning of some particle events. But we cannot select a mission year and know exactly which storms will cross the crew's path. A shelter can reduce exposure. It cannot turn a severe event into a known quantity. Then, there are the questions of hardware and group life. Will the ascent vehicle behave as expected after long storage on Mars? Will 6 people remain cohesive through 3 years of confinement and changing roles? Will pumps, seals, filters, crops, and power systems keep working through actual cold, dust, and repairs? Each question has tests behind it. None has a complete Martian answer. And then come the unknown unknowns. These are not risks we have measured poorly. They are conditions we have not identified at all. The moon offers a useful warning. Before the first landings, robotic missions and remote observations had prepared the way. Yet crews and engineers still encountered surprises in the texture of the surface, the behavior of dust, and the real thermal environment. Mars will not repeat the moon. Its atmosphere, gravity, weather, and distance make it another world entirely. But the lesson carries across. A model can prepare explorers for the questions it contains. It cannot prepare them for every question reality will ask. That is the major reveal. Analysis can reduce uncertainty. It cannot guarantee return. The models have limits. The bodies have limits. And the mission will discover some of both in real time. Uncertainty is not a reason for artificial optimism. It is not an automatic argument for cancellation either. It is a demand for plain disclosure. The people who volunteer would need the best estimates, the established dangers, the reasonable inferences, and the blank spaces placed before them without softening. There will probably be people willing to go. Exploration has never lacked for capable volunteers. The harder question belongs to the institutions that choose them. Will they describe the risk honestly enough for consent to mean anything? Honesty about the risk is only half of consent. The other half is the mind receiving it. That mind has to carry the answer for years. NASA and the European Space Agency, ESA, already select people with unusual strengths. A candidate must be technically capable, physically fit, psychologically stable, able to work with others under pressure. Those demands are real, and Mars would not loosen any of them. But Mars adds another requirement. The person has to accept that everyone and everything familiar may remain physically beyond reach. That is not simply courage. It is endurance of separation. Spaceflight has always involved the possibility of death. The source for this story cites 18 people who died during training or flight. Enough people to fill nearly 2 rows in a small classroom. That loss is grave, but death ends experience. Non-return could mean something different. It could mean continuing to wake up in the same habitat, beside the same small group, while Earth becomes a place you can see but may never touch again. The distinction matters because the mind prepares differently for an ending than for a life that keeps going. Someone can accept a chance of dying during a dangerous mission. They may still struggle with the possibility of decades of ordinary days after the return route has closed. Think about the shape of that experience. A family message arrives late, a crisis at home unfolds without you, a birthday, a birth, a funeral, a changing city, all of it continues beneath the blue atmosphere of Earth. You remain on Mars. The work still needs doing. The air still needs checking. The people beside you are still the people who must help you through the next alarm. This is not a test of bravery. It is a test of duration. So what kind of person could live inside that knowledge without being consumed by it? The answer is not someone who never feels fear, grief, or doubt. That would be denial. The useful trait is psychological flexibility, the ability to experience difficult thoughts and feelings without letting them seize control of every action. A psychologically flexible person can feel homesick and still repair a water pump. They can feel frightened and still follow a procedure. They can be angry with another crew member and still return to the relationship after the immediate conflict has passed. The feeling is real. The feeling does not become the whole environment. Purpose matters just as much. The strongest candidate may need a reason for being on Mars that is not borrowed from applause on Earth, or from the idea of heroic sacrifice. Scientific work, engineering work, the slow construction of a place where later people might live. A problem worth returning to every morning. That is intrinsic motivation, meaning that comes from the work itself rather than from a reward or approval outside it. Without that inner reason, monotony can become corrosive. The same meals, the same walls, the same maintenance tasks, the same small horizon. A person can endure an emergency because it changes from minute to minute. Monotony offers no such urgency. It asks whether attention can remain alive when nothing dramatic happens. And that brings us to the social balance. It is tempting to assume the most solitary person would do best. A person with little need for company might appear protected from loneliness. But extreme introversion can become withdrawal. Withdrawal means pulling away from the only support network available. On Mars, that network is not optional. The opposite extreme is difficult too. Someone who depends heavily on a wide circle of friends, family, and constant new contact may find the narrowing of life especially painful. A tiny crew cannot provide every kind of conversation, affection, disagreement, or comfort that a whole planet once offered. Not maximally social, not maximally solitary, socially balanced. The ideal person would be able to form genuine bonds in a very small group. They would need to draw support from those bonds. They would also need to repair them. On Mars, a disagreement cannot simply drift into distance. The other person is still at the next meal, still on the next repair shift, still part of the system keeping everyone alive. Earth has offered useful partial models of this life. Cloistered monks live within deliberately small communities. Researchers at Antarctic stations can spend years in remote places. Submariners live on long patrols inside confined vessels. These experiences teach us about routine, isolation, conflict, and purpose. But each of them carries an exit. A monk can leave the community. An Antarctic researcher knows that Earth remains under the same sky, and that evacuation is possible in an extreme case. A submarine eventually surfaces. The Mars Desert Research Station in Utah and HICs in Hawaii can simulate schedules, spacesuits, and isolation. Their participants know the door can be opened. On Mars, the world outside the door can kill you. That changes the meaning of confinement. It changes the meaning of a bad day. It changes the meaning of an argument. A simulation can approach the shape of the problem. It cannot reproduce that final knowledge. Mars 500 came closer than most. In Russia, 6 participants lived inside a sealed mission simulation for 520 days, a full year followed by nearly 5 more months. The study did not send anyone to Mars, but it watched what prolonged confinement did to people sharing one artificial world. Sleep worsened over time. Some participants became more sedentary, meaning they spent less time active and moving. Some withdrew socially. 3 people developed patterns of inactivity or withdrawal that would be concerning on a real mission. 2 remained highly active throughout. Same enclosure, same duration, different outcomes. That is the revealing part. The environment matters, the individual matters, and the relationship between them matters too. No interview can fully expose that relationship. No psychological test can prove how a person will feel when Earth is no longer an accessible home. Simulated missions can reveal habits, conflict styles, sleep patterns, and problem solving. They cannot show whether acceptance on Earth will survive the moment when distance becomes permanent in practice. There is another problem. Many astronaut systems have been built to identify people who excel during short, intense missions. That makes sense for launch, spacewalks, emergencies, and demanding work in orbit. Acute challenge rewards focus, skill, and calm action under pressure. Mars asks for those qualities. Then it asks for something slower. Years of uncertainty. Years of repetition. Years without resolution. A person who shines in a crisis may erode under long monotony. A person who appears quiet in an interview may be resilient, or may be retreating. A confident promise to accept non-return may reflect understanding, or it may conceal denial that only distance can uncover. We do not know which tools will predict the difference. We do not know how to identify durable engagement before the real mission begins. And we do not know whether 6 carefully chosen people will remain compatible after years of shared work, shared fear, and shared repetition. That uncertainty does not make selection pointless. It makes it one of the most important parts of the mission. The first crew would need more than skill, more than fitness, more than a willingness to leave. They would need a mind that can make a home within an unfinished world. And the body that carries that mind may be just as difficult to choose. The body looks easier to measure than the mind. That does not make the decision simpler. A Mars crew can arrive with the same training, the same exercise plan, and the same careful medical screening. Their bodies may still travel very different paths. One person may lose bone faster. Another may be more vulnerable to radiation damage. Another may develop changes in circulation, immunity, or vision that no pre-flight test fully anticipated. This is individual variation. It means people do not respond in the same way to the same conditions. On Mars, that variation may decide who can use the return vehicle and who cannot. Conventional fitness is not enough. The strongest looking candidate is not necessarily the most durable one. A body can perform well on Earth. It can still have a weakness under radiation, reduced gravity, confinement, and demanding work. That is the first difficulty. We are not selecting a generic astronaut. We are selecting a particular body for a particular journey. Age makes the problem more visible. Bone mineral density is a measure of how much mineral strength is packed into bone. It is part of the reserve before bone becomes fragile. Consider two people. One leaves Earth at 45 and returns at 48. Another leaves at 30 and returns at 33. Both have spent approximately 3 years away. Both have lived and worked in Mars's 0.38 g gravity. Both may have followed the same exercise routine, but their starting points are different. In the sources model, the 45-year-old could return with bone density more typical of someone between 55 and 60. That is an illustration, not a forecast for every person. Exercise may help. Starting condition matters. The exact effect of reduced gravity over a full mission remains unknown. Still, the direction of the concern is clear. An older candidate may begin with less bone reserve and with age-related loss already underway. The younger candidate may have more room before reaching a clinically serious threshold. Clinical means serious enough to affect medical decisions, not an old body failing on schedule, a reserve meeting, an unfamiliar environment. But youth does not settle the choice either. A younger person may adapt more flexibly to new physical conditions. They may also be in the years when ties on Earth are growing most rapidly. Parents may be aging, siblings may be nearby, a partnership may be new, children may be hoped for or already present. An older candidate may carry more biological risk. They may also have more settled values. They may have a clear idea of what they are willing to leave behind. They may be more ready to accept permanent separation if the return route disappears. So age pulls in two directions: physical reserve on one side, readiness for separation on the other. Neither can be reduced to a simple score. Sex creates another trade space. The source explains that women may be more susceptible to radiation-induced cancer for a given dose. Susceptible means more likely to be harmed by the same exposure. This is one reason the career radiation limits cited earlier can be lower for women. That fact needs to be said plainly. It also needs to be understood plainly. It does not mean women are less valuable to a Mars mission. It does not mean men are safer in every way. It does not tell us who would be the better engineer, scientist, pilot, doctor, or companion inside a small habitat. The risk is system-specific. It belongs to one part of the medical picture. Women may have lower rates of some cardiovascular problems associated with spaceflight. Cardiovascular means involving the heart and blood vessels that carry blood through the body. So the same candidate can face a higher concern in one system and a lower concern in another. Not a better sex, not a worse sex. Different bodies, different exposures, different trade-offs. That is when the pattern broke. The better we become at measuring those trade-offs, the more difficult the selection may become. Genetic profiling may someday add another layer. A genome is the full set of inherited biological instructions in a person's cells. Profiling means looking through those instructions for variants, small differences in the code that may shift how a body responds. Some variants could be associated with repairing radiation damage. Others could be associated with bone loss under reduced mechanical load, meaning a reduced force on the skeleton. Others might influence cardiovascular adaptation. Others might be linked to SANS, spaceflight-associated neuroocular syndrome, the changes involving fluid, pressure, and the optic nerve that can affect vision. The promise is obvious. If a test could identify a person with a much higher risk of severe vision damage or radiation injury, mission planners might protect that person by not sending them. If another candidate carried a variant associated with a greater resistance, the mission might gain a safer margin. That can look like simple triage. Triage means sorting people by risk when difficult choices have to be made. It may prevent irreversible harm, and yet the same test could close a door before the candidate has had any chance to choose. Not just a medical forecast, a rule about who is allowed to go. Suppose a competent adult understands the risk. Suppose the evidence says their chance of vision damage is higher than another candidate's. Should that person be excluded from the most consequential journey of their life? Or should informed consent allow them to accept the danger? Informed consent means agreeing to a risk after receiving a clear account of what is known, what is inferred, and what remains unknown. It respects autonomy, a person's ability to make serious decisions about their own life. But a Mars mission is not only private. A crew depends on every member. A medical decline can change workloads, use supplies, affect the return plan, and place other people in an impossible position. The institution that sends a volunteer also has a duty of care, meaning a responsibility not to expose someone to avoidable harm. This is the ethical knot. Autonomy says an adult should have a voice in accepting risk. Fairness says no one should be excluded carelessly because of biology. Mission duty says the crew cannot ignore a risk that may endanger everyone. There may be no rule that satisfies all three. Genomic discrimination is the name for exclusion based on genetic information. It could appear as caution. It could appear as protection. It could also decide that a person is too risky before they have ever been given the opportunity to demonstrate their skill, judgment, or willingness. The uncomfortable possibility is that safer selection and fairer selection may not always point in the same direction. A protective variant might save a life. A high-risk variant might exclude someone from a historic role. The numbers may become more personal. The decision may become less simple, and none of this produces certainty. Genetic information changes probabilities. It does not reveal a fixed future. A probability is a shifted chance across many possible outcomes, not a promise about one person. Some members of a first crew may preserve enough bone, vision, and cardiovascular function to return in reasonably good health. Others may decline far more. Their return might become medically inadvisable. Their recovery might be long. It might be incomplete. The difference could be profound. Same mission, same destination, different biological outcomes. We do not yet know how to predict that difference reliably before launch. We do not know how age-related reserve will interact with exercise and years in partial gravity. We do not know how to use sex-linked risks without turning them into exclusion. And we do not know where institutional duty should stop and a capable adult's choice should begin. Behind every chart of risk is the place that made the chart necessary, waiting outside the airlock. That place is waiting outside the airlock. It is not a blank red desert. Mars has ancient cratered ground. It has younger volcanic plains. It has polar caps, deep chasms, drifting clouds, dust devils, and storms that can spread across a whole planet. A person selected through all those risk curves is being selected for this world. One part of it would feel unexpectedly familiar. A Martian soul lasts 24 hours and 37 minutes. A soul is one complete Martian day. It is only 37 minutes longer than the day that shaped our sleep, hunger, and waking attention. That is one of Mars's few small mercies. On the International Space Station, the crew can see 16 sunrises and 16 sunsets in 24 hours. The light keeps changing. The body has to be coached toward a rhythm. On Mars, the sun would rise and set at a pace much closer to home, but the day would not look like Earth. Near sunrise and sunset, suspended dust can give the sky a butterscotch color. By day, it may look brown or pink. The rocks may have shapes we recognize, worn surfaces, layered faces, fractured edges. Yet they carry reds and ochres from iron oxide, the same kind of mineral that gives rust its colour. Familiar forms, alien colours, a familiar day, an unfamiliar world. The horizon is slightly closer on the smaller planet. Its curve becomes easier to notice. Above it, thin clouds may form from water ice or carbon dioxide ice, frozen water or frozen carbon dioxide high in the atmosphere. At night, the thin air scatters little light. The stars could appear with the clarity of the highest, driest observatories on Earth. Then comes the silence. Mars can show you weather without letting you hear it. Wind can lift dust and sweep it across the ground. But the atmosphere is too thin to carry sound efficiently. A visible storm may move over the plain with almost no voice at all. Inside the suit, the loudest things may be your own breathing. Pumps, fans, the soft movements of equipment, a voice from another helmet. Outside, no leaves would stir, no birds would call, no distant traffic would fade across the ground. Humans evolved inside biological sound, wind through vegetation, water, insects, other people somewhere beyond sight. Mars removes that entire layer of background life. We do not yet know what years of that silence would do to attention, comfort, or memory. The cold would be present too, even when the suit is working perfectly. Heated layers keep the astronaut alive, but only centimeters of material separate skin from lethal temperatures. On Earth, winter discomfort usually has an exit. A building, a car, a warm room. On Mars, a damaged suit turns cold from an inconvenience into an immediate emergency. And then there is the dust. Martian dust particles are on the order of 1 micrometer. A micrometer is 1/1,000,000th of a meter, a scale too small to notice one grain at a time. Together, those grains can become a constant engineering problem. They are electrically charged, they cling to surfaces, they work into seams, they coat solar panels, they settle on suits, they gather around seals, airlocks, and visors. They can reduce power, obscure vision, and enter the spaces meant to keep people safe. Some dust also carries perchlorates, reactive salts that are toxic enough to matter inside a habitat. Dust does not need a dramatic failure. It can win slowly. 1 seal, 1 visor, 1 panel, 1 repeated trip through an airlock. The larger storms make the problem clearer. A global dust storm can keep sunlight low for weeks or months. Opportunity? The solar-powered rover survived 2 major dust storms. Then came the global storm of 2018. The rover did not lose because its sensors were weak. It did not lose because Mars became suddenly unreachable. Its solar power stayed too low for its electronics. The mission ended in a world where the sun was still there, but the usable light had gone. That is why a human base cannot treat solar panels as its only lifeline. Nuclear power, energy released by splitting atoms in a controlled reactor, would give the habitat a source that does not vanish when dust covers the sky. The field scientist can only walk outside because the quiet machinery inside continues to run. And outside is a record almost beyond measure. Mars preserves terrain from the early solar system. The ancient highlands are covered in craters, marks left by impacts during the violent early era of planetary formation. Far away rises Tharsis, a volcanic region on a continental scale. It supports the 4 largest volcanoes in the solar system. Then there is Valles Marineris. It is longer than the continental United States. In places, it is deeper than the Himalayan peaks at all. Not a narrow scar, a planetary wound. Its story is written through stretching, collapse, erosion, and volcanism. Volcanism means activity driven by molten rock. Each process leaves a different trace. Each layer gives a different clue about how Mars changed across billions of years. The most important clues may lie where water once stayed. Jezero crater held a lake about 3.5 billion years ago. Its delta, the fan of sediment where a river entered standing water, remains visible. So does the outlet channel where the lake eventually drained. That geometry matters because it identifies a place where water carried material in, sorted it, buried it, and may have preserved it. Gale Crater tells a related story. Curiosity found evidence for a complex lake system with neutral pH water that was neither strongly acidic nor strongly alkaline. The system may have persisted for millions of years. Such conditions are more compatible with life as we know it than water at either chemical extreme. Something else was happening. The strongest reason to send people is not that robots are helpless. Robots can see wavelengths beyond human sight. They can sample carefully. They do not need food, sleep, or relief from isolation. In many ways, they are more patient than we are. The human advantage is something narrower. Context, judgment, the ability to notice an unexpected layer, kneel beside it, change the plan, and follow the question immediately. Imagine a person walking into an ancient channel at Jezero. They see a pattern in exposed strata, layers of rock laid down at different times. A rover could measure those layers with extraordinary care, but a trained geologist can combine the pattern with the surrounding slope, loose fragments, mineral veins, and the shape of the channel in a single moment. Then the plan changes, the route changes, the sample changes, and the investigation follows the surprise while its context is still visible. Not superior senses, not superior endurance, immediate meaning. That does not guarantee a biosignature. A biosignature is evidence that may have been made by life. It could be a fossil microbe, a particular organic pattern, or a chemical ratio that geology alone struggles to explain. We do not know yet whether Mars preserved such evidence, or whether a human observer would recognize the decisive clue. But this is what the risk makes possible. A person can stand in a place that was once wet, read its rocks as a changing story, and pursue a question before the next communication delay or programmed sequence slows the search. A clue in one rock may take hours to follow. The larger investigation may take a lifetime. That is why Mars cannot be treated as a destination reached by one launch. The landscape remains after the launch window closes. The samples remain. The machines remain. The questions remain. NASA, SpaceX, China, and other programs have placed crewed Mars ambitions somewhere in the 2030s. Some Chinese planning has reached into the 2040s. A mission around 2035 is a useful way to imagine the sequence. It is not a promise. Large space programs have a long history of moving beyond their first dates. The Space Shuttle was planned to fly in 1978. It first flew in 1981. 3 years, long enough for a small child to begin school. The International Space Station was meant to be complete in 2002. It was completed in 2011. 9 years, enough time for a child to move from early school toward adolescence. The James Webb Space Telescope was once planned for a 2007 launch. It launched in 2021. 14 years, the span in which a newborn becomes a teenager. Those delays do not mean the projects failed. The shuttle flew, the station was built. Webb is returning to remarkable views of the universe, but Mars is harder than any of them. It requires launch vehicles, deep space transit, surface landing, long-duration life support, local resources, a return system, and people healthy enough to use it. So a date on a planning chart is only the beginning. Sustained funding matters. Political support matters. Years of quiet engineering matter. A crew cannot reach Mars on enthusiasm alone, and much of that work happens before anyone leaves Earth. Robotic precursors, uncrewed machines sent ahead, would spend the better part of a decade examining a landing site. They would verify water or other useful resources. They would establish communications. They would deliver supplies. They would position the Mars ascent vehicle, the rocket meant to carry people from the surface to orbit. Then the critical systems would have to run. Pumps, power units, water extractors, storage tanks, communications links. The first crew should arrive after those systems have operated in the real dust and cold, not merely in a clean test room on Earth. That changes the meaning of the first landing. It would certainly include geology. It could include the search for ancient life. But its first job would be survival, not a mature settlement, a proof of life. The crew would confirm that the stored equipment still works. They would expand habitat modules. They would make baseline geological observations. the first careful record of what the site is like before years of human activity alter it. And they would learn how bodies and machines actually behave through Martian dust, cold, 0.38 G, and communication delay. This is engineering proof in its most serious form. A design on Earth becomes a lived system on Mars. The difference can be small, it can also decide everything. If that first crew establishes a working foothold, the next opportunity comes about 26 months later. A second mission could overlap with the first crew's departure. It could arrive after the earlier crew has left. Either way, it inherits more than a habitat. It inherits repairs. It inherits routines. It inherits the local knowledge of which seal gathered dust, which procedure took longer than expected, and which piece of ground offered the clearest path to the next question. By a third or fourth mission, perhaps in the early 2040s if the cadence holds, the place could begin to resemble an outpost rather than an expedition camp. Habitat space could grow, water extraction could become more practiced, small food production could contribute to daily life, operational knowledge could pass from one crew to the next, but none of that is automatic. A delayed launch, a reduced budget, or a political decision on Earth could interrupt the sequence. Mars does not become permanent because a brochure calls it permanent. It becomes permanent only when the chain of missions keeps arriving. Then comes the quieter threshold. Imagine the second or third crew preparing to leave. The return vehicle is ready. One person has a valid seat. The route home exists. And that person decides to stay. Not because the return door closed, because the work continued. Perhaps there is a geological layer still being traced. Perhaps the next 26 months offer continuity that no rotating visitor can replace. Perhaps attachment has formed to the crew, the work, the red ground outside, or the strange rhythm of daily life under a smaller sun. We cannot know which reason would matter most. The decision need not be an abandonment. It could be deliberate, supported by the crew and the institutions that sent them. A person remains. The ship departs. Mars becomes inhabited. That is a small sequence of actions. Its meaning is enormous. The first long-term resident would be watched by people across Earth. Their name, their decision, and their first years on Mars would be recorded in detail. Many founders on Earth disappeared into incomplete history. This one would be known almost immediately. Yet the most lasting influence might be ordinary. Safety habits, ways of resolving conflict, rules about who takes the difficult task, expectations of privacy, shared work, repair, and obligation. These choices would become the first culture of Mars before anyone sat down to write a constitution. The effects would reach far beyond the habitat. In 1969, Apollo 11 drew an audience of about 530 million people, roughly 1/6 of humanity at the time. A first Mars landing would unfold in a far more connected media world. It might be watched even more widely. We do not know whether it would create unity, argument, indifference, or all three at once. International cooperation could matter here. A landing supported by many nations could feel less like a national demonstration and more like a human event. Apollo briefly gave many people that feeling. Mars could create it again. Or it could reveal how difficult shared purpose has become. The scientific result could be just as consequential. A biosignature might appear in an ancient lakebed. It could be fossil microbes. It could be complex organic patterns, carbon-based molecules arranged in a way that may point beyond ordinary geology. It could be an isotope ratio, a comparison between slightly different forms of the same element that can preserve traces of biological activity. Such evidence would not merely add another specimen to a museum. It would change the question of life itself. Life may have begun twice in one solar system. Biology may be a wider tendency of matter than we had understood. But the other result matters too. Imagine a Mars that once held lakes, sediments, and conditions that appear favorable. Then imagine years of careful sampling returning no convincing sign that life ever took hold. No fossil. No clear biological pattern, no chemical trace that survives scrutiny. That would not prove the galaxy is empty. It would not prove Mars was lifeless everywhere and always. But it could suggest that the step from chemistry to life is rarer than we hoped. The absence would carry its own weight. Either way, the people who remain would become custodians of a place no one else can understand in quite the same way. They would send data, images, and observations to Earth. They would share interpretations shaped by years of watching the same rocks, the same weather, and the same machines endure. In that sense, they would resemble scholars who give decades to one question, or quiet communities that preserve knowledge across generations. But Mars would remain different. Its custodians would not be withdrawing from the world. They would be extending the human world into a place that had never held us before. Their knowledge would travel home as signals. Their lives would remain with the landscape. A settlement becomes something deeper when the people living there are no longer all visitors from somewhere else. That depth changes when a settlement must imagine a child. A sequence of Earthborn specialists can rotate through Mars for years. A community cannot remain only that. Sooner or later, the question is not whether adults can endure the planet. It is whether new human lives can begin there. We have no human answer. No one has conceived, carried, given birth, or grown through childhood at 0.38 G. We do not know whether conception would proceed normally. We do not know whether an embryo would develop normally. We do not know whether a child would become a healthy adult. That absence is not a missing footnote. It is the central fact. Consider the length of a pregnancy. 9 months. 3 seasons passing inside a habitat on another world. During all that time, the developing body would live under Mars's lower gravity and its higher background radiation. Radiation is a teratogen at sufficient dose. That means it can interfere with normal development before birth. A mother's body provides the same immediate layer of shielding tissue that it does on Earth. But Mars has no thick atmosphere or global magnetic field above the habitat. More radiation can penetrate the shelter. How much reaches developing tissue and what it means over a full pregnancy remains uncertain. This creates an ethical problem with no comfortable side. One path would prohibit reproduction until there is enough evidence to estimate the risk. The other would allow it, then learn from real outcomes. The first limits a fundamental human choice. The second makes an embryo or fetus part of an unprecedented experiment without consent. Parents could accept danger for themselves. They could not fully accept it for a child. Planners could write rules. They could not base those rules on direct Martian evidence, not a routine medical decision. A boundary between protection and control. A temporary restriction during the earliest, most fragile years might be defended as emergency caution. Indefinite reproductive control would be something else. It would ask adults to build a permanent home while denying them one of the ordinary ways human homes continue. We do not know where a defensible threshold would lie, because no human being has yet supplied the data. Then comes the body itself. A child born on Mars would still be human in every genetic sense, but development is plastic. It adjusts while a body is growing. Bones may form for the loads they repeatedly carry. The circulation may learn to move blood through a world with lower gravity. Proprioception, the quiet sense that tells you where your body is without looking, may learn a different relationship between balance, effort, and falling. Earthborn adults arrive with bodies built at 1G. They may adapt partly to Mars after they land. A Mars-born child would be shaped before birth. Then, through every step, fall, lift, and heartbeat of growth. Mars would not merely be where that child lived. It would be the reference setting of the body. The answer was stranger than expected. Earth could become the difficult environment. Moving from 0.38 G to 1 G would mean about 2.6 times the gravitational load a Mars-born body had always known. More than double the familiar pull. Every step would cost more. Every upright minute would ask more of the heart and bones. Fighter pilots can tolerate several G, but only briefly. A sharp maneuver is not a lifetime. An Earth visit could resemble asking someone to live continuously under more than twice the weight their body had been built to carry. Not a harder vacation. A possible medical ordeal. not an adventurous trip, a world that may require major support just to inhabit. This is an inference, not a proven prediction. We cannot say that every Mars-born adult would be unable to live on Earth. We cannot say when support might be enough. But the direction of the problem is clear. For the first generation, non-return may be a risk. For the next, it may become biology. And the difference could appear before any new human species exists. Environmental separation can change bodies long before genes divide into separate lineages. One generation may ask whether it wants to return. The second may ask whether it can visit. By a third, Earth might be survivable only with extensive medical help. The source calls this a biological Rubicon, a point after which going back becomes much harder. It suggests the threshold could come within a century of the first landing. That is a possibility, not a timetable, yet it names a profound shift. For roughly 300,000 years, the span of about 3,000 century-long human lives, Homo sapiens has lived on one world. People crossed deserts, mountain ranges, and oceans. They carried languages and tools into every climate, but they remained beneath the same gravity and air. Polynesian navigators crossed thousands of kilometers of open ocean in outrigger canoes, small boats with stabilizing side floats, without charts. Their achievement remains remarkable, but the islands they reached stood beneath the same sky. Their bodies could breathe the air. Their crops could grow in the soil. Mars offers no such land. Its pioneers must manufacture habitability, pressure, air, heat, water, food, radiation shelter, the repair knowledge that keeps all of it working. And then, there is the old pattern of settlement. A first landing can prove that people can arrive. It cannot prove that people will be sustained. Vinland, the Norse settlement in North America, lasted about a decade, the length of a child moving through most of primary school, before it was abandoned. Roanoke disappeared, without a confirmed account of what happened to its people. Mars could fail more quietly. Imagine a first crew and then a second crew arriving. Imagine 3 or 4 residents still maintaining the base. Then a third mission is cancelled by cost, politics, or another priority on Earth. Supplies begin to narrow. Essential parts begin to fail. The settlement has not been defeated by Mars in a single moment. It has been left behind. The Moon offers a modern warning. 6 Apollo landings happened across 3 years. Then people did not return to the lunar surface for about 50 years, longer than many working lives. The mission succeeded. The continuity did not. Mars requires a different kind of success. Not one landing, not one celebrated return. A chain of support that remains present after the first public moment has faded. Medieval cathedrals offer a useful comparison. Their builders began work they knew they would not complete. Later workers continued it. Still later, generations finished structures whose founders had become history. Mars asks for that kind of inherited purpose. Governments would need to sustain budgets beyond an election. Companies would need to sustain hardware beyond a short commercial horizon. Engineers and doctors would need to pass on knowledge beyond a single career. The difficult system may not be the rocket. It may be the institution that keeps deciding the rocket, the medicine, and the next crew are still worth supporting. NASA's framework is called Moon to Mars. Artemis is intended to return people to the Moon and build a sustained presence there, using the Moon as a proving ground. Gateway is a small planned station in lunar orbit, meant to support and stage deeper missions. In the source's mid-2020s planning context, Artemis 3 was a target for a human lunar landing. NASA also discussed Mars missions in the late 2030s or the 2040s, but no final Mars architecture, crew size, duration, or landing date had been settled. The path depended on Artemis results, deep space propulsion, and funding. Those are not minor details. They are the mission. SpaceX presented a more definite public picture. In the source's planning context, it named an uncrewed Mars flight in 2026 and a crewed attempt in 2028 or 2029. Outside interpretations placed a crewed mission in the early 2030s at the earliest. These are ambitions, not completed milestones. Starship is designed to be reusable and to carry about 100 metric tons to low Earth orbit, roughly the mass of 50 small cars. That scale could carry meaningful supplies and habitat equipment. But a Mars flight would also need reliable orbital operations, refueling in orbit, and deep space navigation. At the source point, those full capabilities had not yet been demonstrated together. Rapid testing can produce visible failures and later successes. That is how an engineering program learns. It is not proof that a vehicle is ready to carry people across interplanetary space. China has also described crewed Mars ambitions in the 2030s and 2040s. Its Chang'e program has landed on the moon several times, including the far side. Long March 9 is being developed as a heavy-lift rocket, yet sustained funding for a human Mars effort cannot be confirmed from outside the program. ESA, JAXA, and other agencies remain important through robotic science and possible partnerships. But cooperation can be fragile. ExoMars was disrupted after Russia's 2022 invasion of Ukraine broke European and Russian cooperation. A Mars settlement would depend on technical links. It would also depend on political relationships that can change far from Mars. Then comes the cost. Apollo required about $25 billion in 1969 dollars, perhaps $200 billion in current value, spread across about a decade. The later figure is the cost of building a project for the length of a child's school years, then carrying its support beyond them. Estimates for a first human Mars program range from $100 billion to more than $1 trillion. The upper end is 10 times the lower one, and development may take 15 to 20 years, long enough for a child born when planning begins to become an adult before launch. Constellation, an earlier NASA Moon and Mars program, was cancelled in 2010 after 6 years and about $9 billion. Commercial rockets may reduce the cost of reaching low Earth orbit. They have not yet demonstrated cheap human travel into deep space. The numbers are uncertain. The commitments are not. Mars's children would depend on more than successful birth. They would depend on transport continuing, medicine continuing, knowledge continuing, and the quiet redundancy of a civilization that does not leave them alone. All of that continuity rests, at first, on whether the route between worlds can work more than once. Return sounds like a single decision. The crew boards a rocket. The rocket leaves Mars. Then everyone comes home. But return is not one maneuver. It is a chain. The first link waits on the surface before the crew ever arrives. It is the Mars Ascent Vehicle, or MAV. This is the small rocket that must lift people from Mars into orbit. It has to be light enough to leave Earth, land safely, and stand ready for years. Then, on one required day, it must work. Mars does not store machinery gently. The temperature can move from -60 to +20 degrees Celsius. That is colder than a household freezer, then as mild as a room. Dust works into every exposed place. Ultraviolet light, the part of sunlight that can damage materials, slowly weakens polymers, the tough plastics used in seals and wires. Perchlorates, reactive salts in Martian soil, can corrode some metals. So the waiting rocket is not simply waiting. Its valves are waiting. Its seals are waiting. Its tanks, lines, computers, and ignition systems are waiting. And each must wait correctly after years in the cold. Then comes the fuel. The NASA concept described here would make liquid oxygen and liquid hydrogen on Mars. Liquid oxygen is oxygen cooled until it becomes a fluid. Liquid hydrogen is hydrogen cooled even further into the same form. Carrying all of that propellant from Earth would make the outward launch far heavier. Making it locally saves that mass. It also moves the risk. This is called in situ resource utilization, or ISRU. It means using local material instead of bringing everything from home. The plant must gather air or water-bearing material. It must process it. It must separate and convert it. It must store the fuel at cryogenic temperatures, cold enough to keep those liquids from boiling away. It must monitor every part. And it must build up enough propellant before anyone closes the hatch. Not a tank already filled. A factory that must keep working. If that factory falls short, the return vehicle is still on Mars. So are its passengers. Suppose the MAV does rise. The crew has only reached the next vulnerable stage. In Mars orbit, they must find and dock with an Earth return vehicle, or ERV. That is the largest spacecraft waiting in orbit, or arriving there on schedule, to carry them back across the space between the planets. Rendezvous is the careful act of bringing two spacecraft to the same place and speed. Docking is the final connection between them. Near Earth, mission control can guide a crew through trouble almost as it happens. Near Mars, that kind of help is impossible. Signals take time to cross space. The crew and their onboard systems must navigate, judge, and complete the docking where they are. Miss that meeting, and the problem is immediate. No surface below, no route home. The ERV may still be nearby. It may be visible. It may contain everything the crew needs. But without a successful docking, it remains unreachable. Even a clean departure from Mars does not finish the journey. The homeward transit takes about 8 or 9 months. That is another full season of mission life after the crew has already spent years managing Mars. The ERV needs air, water, food, medicine, power, and thermal control. Thermal control means keeping equipment and people within a safe temperature range. It needs to keep the crew healthy while their bodies continue responding to low gravity, radiation, confinement, and fatigue. A round-trip message can take as long as 44 minutes. Mission control remains present. It cannot be immediate. The vehicle must become a small moving home. Again. Then the blue world grows larger, and the highest physical demand may still be ahead. Earth entry means falling into a thick atmosphere at enormous speed. A heat shield protects the spacecraft by taking the intense heating first. Parachutes, retro rockets, or a combination of both must slow the capsule enough for landing. All of this must work while the people inside endure their greatest gravitational load in years. Their hearts have adapted to a lower demand. Their bones and muscles may be weaker. Their balance system has learned weightlessness and Mars gravity. Their nervous system has learned a different ordinary world. Now, Earth asks for everything at once. Hardware must hold. Bodies must hold. Timing must hold. That is why a return cannot be described by one reassuring test. Each stage can look reliable on its own. Each stage still has some chance of failing. When the stages must happen in sequence, the complete mission becomes less certain than any single demonstration suggests. Think about a chain of small chances. One weak link matters. Then another. Then another. The honest calculation has no comforting final percentage yet. It is not known. Not because engineers cannot calculate. Because no one has performed this complete sequence with real machines and real people under real Martian conditions. Good design does not demand perfection. It seeks graceful degradation. That means a failure leaves some useful option behind. An ascent vehicle that reaches a lower orbit might still meet an ERV that changes its orbit. An ERV with weaker propulsion might take a longer path home. A damaged landing system might still permit a harder landing that people can survive. Backups matter because they give a mission room to bend. But some failures do not bend. An MAV that never ignites cannot reach orbit. A body that cannot survive re-entry cannot use a seat. A medical emergency beyond the habitat's equipment cannot be solved by patience. Those are not ordinary setbacks. They close the available paths. Another MAV might come, but the next opportunity is about 26 months away, and only if a replacement mission was already being prepared. A launch schedule can replace hardware eventually. It cannot redesign one particular body after the body has crossed its own limit. This is the irreducible part of the problem. The first use of a system can reveal behavior no test found. One person's response to years of radiation, lower gravity, and isolation may differ from another's. No pre-flight model can tell the whole story in advance. That does not mean a crew cannot return. Careful design, serious investment, and good fortune could bring them home. Poor design, inadequate support, or bad luck could prevent it. Both statements are true. Neither is a promise. And still, someone will choose to go. Within the next 2 or 3 decades, Perhaps within the lifetime of people alive now, a trained person may know these risks in unusual detail. The radiation totals, the bone loss models, the long communication delay, the dust storms, the stored rocket, the possibility that home may become unreachable. Then that person may board anyway. Some are likely to return. They may step onto Earth unable to walk without help. Months of rehabilitation may follow. Radiation exposure may remain in their health statistics for the rest of their lives. But they will remember Mars, the red plains, the closer horizon, the russet sky, the hard shadows cast by a smaller, dimmer sun, bright stars with little atmospheric twinkling, their own breathing inside a suit, louder than the nearly silent world outside it. They will have handled Martian soil. They will have stood beside ancient channels and lake beds. They will have followed clues in a landscape where the question of life beyond Earth is written in stone. And when they looked outward, Earth would have been a blue point, changing in distance as the planets moved. Every loved person there, every familiar street, every earlier memory, all of human history in one small light. Others may not return. The reasons will not all be the same. One person might die. Another might become medically unable to make the journey. Another might choose to remain because the work, the place, and the people there have become home. Those who remain do not vanish from the story. They send data. They send engineering reports. They send observations, interpretations, images, private messages, perhaps art. Over time, they learn one landscape across its seasons and storms in a way no brief visitor can. But there is a quiet distance built into every final message. A signal from Mars can take roughly 10 to 20 minutes to reach Earth. If the message reports a death or an unrecoverable failure, the event has already happened when the words arrive. The news travels alone. No one on Earth can arrive quickly. No hand can reach across the delay. The gap between loss and knowledge becomes part of the loss itself. Yet even that knowledge can endure. The people who do not return become founders. Their records reduce uncertainty. Their repairs, mistakes, routines, and discoveries become the practical inheritance of later crews. What one person learns by surviving a difficult Martian winter may help another person remain by choice. And some may rest there. Mars is dry and cold. It has no oceans, little biological erosion, and a comparatively quiet surface. A grave in that soil could remain for thousands of years, perhaps longer than human civilization has existed. Not forgotten by the planet, preserved by it. One day, a person born on Mars may visit such a place. They may understand that their home was not simply built. It was made possible by people who accepted the distance before anyone knew how the story would end. Those who return will prove that human beings can visit another planet and come home. Those who remain will prove something different. That human life can take root on more than one world. The first travelers may be alive now, studying, training, designing systems in laboratories and simulators. Some may step shakily back onto Earth. Some may become the first people to rest in Martian soil. The outcome of each journey will matter profoundly. But the deeper change begins with the going. For the first time, the horizon will not be an edge of Earth. It will be another world, reachable, fragile, and waiting.